So today we're going to go over some Linux disk and file system maintenance tools that I have found very helpful over the years for various events that come up, and just kind of how to manage and go through the various levels of storage and file systems that we have on our Linux-based servers. So one of the first tools, we'll start at the very lowest level on the actual physical drives. One of the very first tools that I like to use is smartmontools. This allows us to actually access the smart data on the hard drive, as well as getting various information from your hard drives and solid-state drives. So we can go ahead and install that. It doesn't come installed by default, but we just say apt install smartmontools, and it will install it there on the server. So the tool we use is smartctl, some smartctl, smartctl, and we would just need to give it a drive. So if we want to get information from a drive, we'll just do smartctl -i to just get information, and let's pull that information from dev SDF on this particular machine. I've connected a couple really old drives actually via a USB connection. Sometimes this tool has a little trouble with USB connections, but it works fine today. So we can see there's a 160 gig Seagate drive, really old laptop drive, and SDG, for example, and there's the drive. It just gives us the serial number, capacity, and lots of useful information from the drive like that. Now let's suppose we wanted to make an inquiry into the health of the drive. Instead of -i, we could do -H, and it's going to give us just one line opinion of whether that drive is healthy or not. So same thing for G, etc. Now, sometimes you might want to do a little troubleshooting on a drive and actually get some information from that. We could go ahead and do, instead of -H, -a, and that's going to give us quite a large printout from this drive. And we can scroll back here through this printout and kind of go through. There's the information. There's the health assessment. There's information about self-tests that the drive has run. And here's just some raw stats from that drive. One I like to look at is this one here, the power on hours. This drive, even though it's old, it's not been run much at all, so 100 hours on the drive. I've seen drives with as much as 50,000 hours on the drive. Other things that you might want to look at is certain things like read error rates. Solid-state drives have information down here that gives you information on what the wear is on the drive. Sometimes those attributes don't always come through with this tool, but you can get lots of information on the drive from here. You can also use this tool to start a self-test. So we would just do smartctl-t. We'll just do a short self-test on SDG and also on SDF, and it'll instruct that drive to perform its internal self-test routines. And here in a couple minutes we'll be able to go and query that and get the results of those self-tests. Alright, we'll go ahead and see if those self-tests have completed. We'll go ahead and just print out all that information for the SDF and SDG. Here, there's SDG, and sure enough, there's the short offline self-test completed without error. As you'll notice, on most of our systems, we use software RAID, and I've demonstrated this on a previous video, but I'll go ahead and demonstrate very briefly setting up a RAID array and then dealing with various sorts of failure events on that array. So I've already actually created a partition on each of these drives. If you can see dev SDF, there's a 5 gig partition, SDF1, and SDG. There's also a 5 gig partition there. I'm going to go ahead and create a small RAID array out of these two small partitions, let that sync up, and then see how it deals with the various failure events. So to do that, we'll go ahead and mdadmin create, we'll go ahead and make this a mirrored RAID 1. RAID devices 2. We'll call this dev md 2 in this instance, and then at dev sdf1 and dev sdg1. And it's going to ask us, yeah, we'll go ahead and continue creating the array, and it's started. So now I can cat proc mdstat, and I can see that it's there, it's already syncing up. It's going to take a couple minutes to finish that. We can use the watch tool to watch and see that go. While that's syncing up, we'll go ahead and create a file system on the array so we can see how it behaves under various failure events. So that should be pretty simple. Make mkfs.ext4, and we'll call that dev md2 is what we called that. Okay, put the filing system on there, and now we'll go ahead and make a mount point for it. mnt md2, and then mount dev md2 on mnt md2, and then we'll go ahead and seed into that directory. So we'll go ahead and create some files in here. 1, 2, 3, 4, 5. There we can see there's several files there. And we'll make a big file, dev 0f equals big dot file. We'll make that 200 megabytes, and we'll just fill that with zeros. And so there, we've got some files there. Let's see if our RAID array is finished syncing up. Okay. Now we have MD2, and you can see there SDG1, SDF1, you can see that it's mirrored. We can go ahead and get some details on that by doing mdadm-detail/dev/md2, and there it's going to show us it's clean, 2 active working devices, etc., and it gives us the full stats like that. Now, whenever we create a new RAID array on a running system, it's a good idea to go ahead and update the running RAID configuration so that when you reboot the system, it comes up with the same device name. Otherwise, as you can see here in that previous command, we've got some inactive RAID arrays here with really kind of some odd names. So in order to update that, there's a tool, it's a rather obscure tool, but it's under user share mdadm mkconf, and that will generate a configuration file which we can then spit out to overwrite our existing configuration file in etc mdadm.conf. So we can go ahead and do that, and then we can use nano to go ahead and edit that file and name those RAID devices how we like them. So you can see here we have dev md0. Now, I usually take these slashes out, I don't know if it's necessary, but with md0, md1, and md2. So now our RAID configuration will be persistent across reboots. One thing I do have to do after this, because we want to have that loaded into the initial RAM disk, is to depackage, reconfigure, and reconfigure the running kernel. And that will go ahead and copy that RAID configuration into the init RAM disk of the kernel. So that will load as soon as the system boots. Now let's go ahead and simulate some different failure events on this RAID array. So again, we can kind of watch to see what's happening here. MD2. I'm going to just watch this, And here we have the detail. It shows clean and everything. And I'm just going to go ahead and pull the plug on one of these hard drives. Notice now suddenly the RAID array becomes degraded. It's still running, but it shows that one of the drives is removed. However, because it was mirrored, we can still access all of these files. You can see I could copy this big file, call it big2.file, and I can still work with these, but we are missing, of course, one of the drives. So we'll have to go ahead and add that drive back in. So we'll connect that drive back to the system, and it might come up under a different drive letter, but we'll see what it does. We can use dmessage to get some idea of what's going on. And notice there at the top here it's showing the disk failure on SDG, and it shows that the RAID is continuing on one device. It's printing out this configuration. Now we've got SDG attached again, so if we look at our MDstat, of course the drive is not automatically re-added to the array. I can look at that drive and make sure the configuration is still the same. SDF, of course, that's the one that we didn't unplug. SDG is the one we actually unplugged. The piece is still there, but we need to re-add that to the array. So this is the important command: mdadm dev md2 add dev sdg1. And that's going to re-add that back into the array. And then if we watch cat proc mdstat, we can see that now it's actually resyncing the array again. Alright, at this point I can see that the array has rebuilt again. So I'll show you another way we can do the same thing by removing a drive from the array without physically disconnecting it from the system. So we would just, again, we'll take a look at our configuration, SDF1 and SDG1. In this time, we'll go ahead and remove SDF1. So we'll do mdadm. First of all, we'll mark it as faulty. mdadm dev md2 fail dev sdf1. Okay, now it's set as faulty. Now I'll run the same command, but this time we will simply remove the SDF1. Alright, now if I take a look at our configuration again, notice SDF1 is no longer there. Even though we've disconnected one drive, reconnected it, and now disconnected the second, notice that our RAID is still there. We can still do plenty of operations in our files. We've never unmounted this file system. So the system continues running. All the files are still there. We can't obviously remove both drives at the same time. We really would lose our files in that case. But if I need to re-add that device back in, just simply mdadm dev md2 add dev sdf1, and then again we can, if we're curious, watch mdadm detail dev md2, and there we can see that it is resyncing. We can see the rebuild status down here, how quickly it's recovering that array. Now that we've gone over some basic operations with the RAID arrays, let's move it to logical volumes. We'll go ahead and unmount this particular file system, and in fact we'll blow it away in our next operation. Usually when I create a RAID array, I don't create a filing system directly on that array. I add it to a volume group and then create the filing systems and logical volumes in that volume group. The first step in creating a volume group is to format the physical volume for use with LVM. So we do that by using pvcreate, and then we'll go ahead and give it the device name, which we just created, the devmd2. Now it detects, of course, that we formatted this as an ext4 file system, so we will go ahead and wipe that, and now it is set up as a physical volume. And we can actually see this by typing pvs, and it will show those physical volumes. Now notice on this system we already have a volume group called VG1. If we didn't, we could use something like vgcreate and VG1 and then give it the names of our physical devices. But we don't have to do that this time because we already have a volume group. So we're going to use vgextend to extend that volume group VG1 and add our devmd2 into that volume group. So vgextend, now if I do pvs again, it's going to show that devmd2 is now a part of the VG1 volume group. Now that we've done that, we can go ahead and create logical volumes with lvcreate. Again, we're going to create them in the volume group VG1. I'm just going to name this particular one test1. And we'll make this, say, a 3 GB volume. And we'll put that on our newly provisioned partition, devmd2. Alright. Well, apparently I typed that wrong. lvcreate VG1. Yes. And that's created. And now we can actually create a filing system on that logical volume. ukfs.ext4 dev mapper vg1-test1, and it's creating that filing system for us. Now I can make a mount point, say mnt test1, and we can actually mount our filing system. Mount dev mapper vg1-test1 at mount point mnt test1. I forgot the 1 there. Dev mapper vg1-test1 at mnt test1. Alright, and then I can actually cd into there and we can create files like we did before. Sure enough. Now we might want to do some maintenance occasionally on our logical volumes. Well, let's go over some commands to get some information. vgdisplay will show the entire volume group and some information about that. For short, VGS. We can use something like pvdisplay to show information about each of our physical volumes, or for short, PVS. I like the PVS version because it does give us down here a nice assessment of how much space is used and how much space is free on each of the different physical volumes. You can see this is basically 5 GB here. We have basically 2 GB free. And then for the actual logical volumes themselves, we can use lvdisplay. That gives us detailed output, or for short, LVS. And now we can see on the system already we've created root and swap, and this is the one we've just created, test1. We can do LVS-O plus devices, and that will add one more column here to show us which device the individual logical volumes are on. We can even add a -A to show us any hidden volumes that might exist on the system as well, which we don't have any at this point. We will before this demonstration is over. Now, suppose that we're working along here and for whatever reason we run out of space. Maybe we made some big files. Let's copy lots of zeros. We'll call it zeros.file. 1 megabyte and count equals 1000. Okay, and we'll call this another file zeros 2. Alright, so now we have a couple big files here. If we show the free disk space, you can see, oh, we've used 73%. Once it starts getting there, I start having to think about enlarging our partition, because we certainly don't want this to run out of space in the middle of a busy day. So let's go ahead and use lvextend to grow that particular logical volume, and we'll go ahead and add 10 gigs to that. Now obviously it's going to have to allocate extents from more than one physical volume in order to do that, but it should be able to do that happily. And sure enough, and if I do LVS again, now it's going to show that. Just out of curiosity, if we do PVS, it's going to show us obviously that MD2 is full, and it's taken some more extents from MD0, it looks like. But anyhow, so we've extended our physical volume, but our filing system isn't extended. So if we do disk free at this point, it's still going to show that the device is only 2.9 gigabytes and it's 73% full. So once we extend the logical volume, we have to use the resize 2fs or some similar command to resize that filing system to take up this full space of the block device. So we'll go ahead and div mapper pg1-test1, and it's going to go ahead and resize that online, show the free disk space, and now you can see the device is now 13 gigabytes and it's only 17% used. Now suppose I wanted to remove this RAID array that we've just created with these external USB drives. For example, that's probably not a good idea to run with these external drives in production. But if I show the configuration of my logical volumes, I can do lvs-o plus devices, and I can see that that test1 volume group now resides on both dev md0 and dev md2. And that dev md2 is the one that is on those USB drives. So I can use something like pvmove and tell the logical volume manager to move all of the physical extents from dev md2 over to dev md1. Well, apparently I didn't type that, right? pvmove dev md2 dev md1. That'll take a little while. We might come back to this in a minute. Okay, at this point you can see that it says it has completed the pvmove. So if I do the lvs command again, it shows down here the devices are MD0 and MD1, but MD2 is out of the equation. And I can confirm that by doing PVS, and it shows that the total size and free size on MD2. I could do PV display dev MD2. That's another way of doing it. I'll show there's no allocated physical extents. So at this point, we can nicely take this MD2 down, just reversing the process. So I'm going to VG reduce VG1 dev MD2. And that's going to remove it. So if I show the physical volumes now, dev MD2 is now stopped. Now, we could remove the formatting from that. So pv remove dev MD2, and that's going to just wipe that off so that it doesn't even show in our list of physical volumes. Then we can use mdadmin to stop that RAID array. And if you see here, the RAID is still running, dev MD2. So if we do mdadm-stop dev MD2, it's going to stop that, and now it doesn't even show. So at this point, we can safely unplug those USB devices, and nothing at the higher levels will complain about it. Boom. Boom. Okay, we've removed our USB devices entirely. As you can see, if I do fdisk-l, it's going to show the various devices, fdisk-l dev, SDF, or SDFDG. Those devices are gone. But of course, our new volume group, or a logical volume, is still running and mounted on the M&T test 1. Now we can, of course, unmount that if we don't need that mounted anymore. And here's a couple other commands that you might find useful. Sometimes, so LV display, VG1, test 1. Sometimes you may have a need to mark a logical volume as not available. That'll take it out of the system as a block device that can be scanned for by other things on the system. So in order to do that, we would simply do lvchange -a, which is available, in, and vg1/test1. Now if we do LV display again, notice it shows LV status is not available. Sometimes, like if we boot up to rescue mode, all of the logical volumes will simply come up automatically in this status, not available. And at that point, if we want to work with those volumes, we would need to use lvchange -a y, and then give it the device at vg1/test1. And then that becomes available again, LV display, and it shows that that's available. Now, if you're really done with a logical volume, you don't need any data on it anymore, and you really want to destroy it, sometimes we do this. We can just simply LV remove vg1/test1. And it's going to confirm, do you really want to remove it? And yes. And there it's gone. If we do LVS, there you can see it's no longer in the list. So that's just a brief overview of some of the different operations you can do with logical volumes. I haven't gone into snapshotting or anything like that, but I will, in the next video, make a short demo on maintaining the LVM cache devices.